My name is Evan Olson, and I'll be solving problem 29 of chapter 12 of the Fundamentals of Heat and Mass Transfer, 8th edition. The problem statement says to consider the diffuse surface in problem 12.28. Determine the surface hemispherical emissivity and emissive power at 300, 500, and 700 Kelvin. And at what wavelength does the peak spectral emission occur when the surface is at these temperatures? This graph here is from problem 12.28 and describes that the surface emissivity with respect to wavelength. We first need to find the surface hemispherical emissivity, which is just going to be found using this integral, which is our wavelength dependent emissivity times our wavelength dependent emission power divided by our total blackbody radiation from 0 to infinity. We are able to split that into multiple integrals depending on this piecewise function here. So we can take the integral from 0 to 4 micrometers, and then from 4 to 6, and then from 6 to infinity, as this continues at 0.5, to get our total hemispherical emissivity. So after splitting those integrals up, we get terms where the emissivity is constant in those wavelengths, so we can pull it out of the integral. So we get our emissivity from 0 to 4 micrometers times the integral from 0 to 4 times our emission power in lambda divided by our total blackbody radiation. This term here is described by an emission factor, which we can find or calculated for us on table 12.2 in the textbook. And this will be the same for the range 4 to 6 micrometers and 6 to infinity micrometers. In order to find those emission factors, we first need to calculate them at every wavelength split in the problem. So we need to calculate at 4 and at 6 and at infinity. So for our 4 micrometer wavelength, we have to multiply the wavelength times our temperature, which is 300 Kelvin for our first case. That gets us a value of 1200 micrometer Kelvin, which correlates to an emission factor from 0 to 4 of 0.002134. The same for 0 to 6 micrometers, we get a lambda T of 1800 micrometer Kelvin, which correlates to 0.039341 emission factor. And from 0 to infinity, it's going to be 1 always. And so in order to calculate our ranges, which are from 4 to 6 and 6 to infinity, all we have to do is to subtract our factor from 0 to 4 from 0 to 6 to get 4 to 6, which turns out to be 0.037207. And from 6 to infinity, similarly, we just subtract 0 to infinity, which is just going to be 1 minus f0 to 6, which we found to be 0.039. And that gets us to a factor of 0.961 almost. And we're able to plug that into this relationship above here to get our final emissivity of 0.4857 at a temperature of 300 Kelvin. Now we follow this process for both 500 and 700 Kelvin. It's the exact same. You find your lambda T for each wavelength, correlate that to an emission factor, which will be different at different temperatures, to get your emissivity value. And so for a temperature of 500 Kelvin, you get an emissivity of 0.434. And for 700 Kelvin, you get 0.441. The second part asks us to find the spectral emission, the emissive power at both 300, 500, and 700 Kelvin. And the emissive power is just going to be our emissivity times Stefan-Boltzmann constant times our temperature to the fourth, which is very simple. Our Stefan-Boltzmann constant is 5.67 times 10 to the minus 8 watts per meter squared Kelvin. And for each of our cases, 300, 500, and 700 Kelvin, we get 223.1 watts. 1538.4 watts and 6013.6 watts, respectively. And finally, it asks us to find at what wavelength does the peak spectral emission occur when the surface is at these temperatures. And this relationship is just described by Wien's displacement law, which is our peak spectral emission, gamma peak, times our temperature, which is equal to a constant. In this case, it is, well, it is always 2,898 micrometer Kelvin. And so at 300 Kelvin, we just plug 300 Kelvin in for T and then rearrange for lambda to get 9.66 micrometers. At 500 Kelvin, we get 5.8 micrometers. And at 700 Kelvin, we get 4.14 micrometers.